Hello, hello. Am I audible?
Yes, ma'am.
Okay. And my screen is visible too, right?
Yes, ma'am.
Okay. Thank you. S- Good afternoon, everyone. I welcome you to the week 7 problem solving session of NPTL course Graph Theory. So last time we began revising network and flow, but we didn't revise it properly. So today's agenda is to study maximum flow in a directed graph or in a special kind of directed graph, which is a network. So let's begin. Um okay. Okay. So first of all, what is a network? So as I said, network is a special kind of a directed graph. What directed graph? So directed graph is just that every edge has also a direction attached to it. And this is a special kind of a directed graph which has two special vertices, source vertex and a sink vertex. Source vertex is basically it's one of the vertex in which all the edges are going out of that vertex, and sink vertex is the vertex in this vertex all the edges are coming in. There is no edge which is going out of the sink vertex. So network is a directed graph which has two special vertices, source and sink, and moreover every directed edge has some integer attached to it, which we call the capacity, a non-negative some non-negative integer. So you can see this is an example of a network. So it has two special vertices, S, T. This is a source vertex. You can see all the edges are going out of this and there is no edge coming into S. And similarly, T is a sink vertex. All the edges are coming into T. There is no edge which is going out of T. And each edge is directed, so each edge has a direction attached to it, like SA has a direction SA. And each edge also has some capacity. So above a edge there is a number mentioned which is the capacity of each edge. So such a data of a graph is what is we called a network. So now, so why is this network there? This network is there, and it has some each edge has some capacity. So our aim is to find maximum flow in this network. So first of all, before, what is flow? So you can see a flow is basically a function which is assigning a real value to each directed edge, and these two rules should be followed. So first of all, we are assigning some number, a real value. Generally we are talking about integral flow, so we take it as a integer. So we are assigning an integer to each direction, and these two rules should be followed. First rule is capacity. So the flow in each edge should be less than equal to capacity. So basically your flow cannot exceed the capacity. So suppose this is the edge SA, and SA has capacity 2. So when you are assigning this some number, it can be either 0, 1 or 2. It cannot exceed 2, and this should happen for each edge, because flow is a function which is assigning a non-negative value to each edges. And second rule is conservation law. So first is the capacity rule and second is the conservation law. Conservation law says that if you take any vertex other than S and T, that is other than the source vertex and the sink vertex, suppose this A, B or C, so the flow coming into A should be equal to flow going out of V. So what do we mean by that? So suppose I am picking up some vertex V which is not equal to S or which is not equal to T, and if I am summing up flow values, so summing up flow values for each edge, which is each edge going out of U, that is my flow out of U, and this should equal uh, to the flow value coming into U. That is basically we are summing flow values over edges which are going into U. So let's understand flow with some example. So I'm taking this. I'm start. This is the old example, that the one G. So this is the network, and now we are trying to assign a flow. Now we are trying to assign a flow to this network. So basically we are trying to see assign a float to this network. So what we have to do, we have to assign an integer to each edge in this graph, and that integers, we have to assign those integers in such a manner. Two rules should be, first of all, we are assigning a non-negative value, and it should satisfy two property. First is the capacity rule, and second is the conservation law. So these are all the edges: SB, SA, BA, BC, AT, CT, and on the first column I have list down all the capacity. Now all the capacity. So now we are assigning an integer to each of these edges, and so I have done this. So I'm assigning these numbers. So I'm assigning float 2. So float 2 to SB, and I can do that because it is less than equal to 3. So I have seen, I have assigned this float to this. But so first rule is satisfied, you can see in all this. Oh sorry, capacity. So flow is less than equal to capacity. So in all the columns you can see the value appearing on left hand side is greater than equal to the value appear on right hand side. So first rule is satisfied, that is capacity rule. Now there is second rule also. What is the second rule? Second rule is the conservation law. Conservation law says that other than S and T, all the we have to check that flow coming into each vertex should be equal to flow going out of each vertex. And you can see this rule is also satisfied by this function. And if these two rules are satisfied this by some function, then we say that that is a flow. So you can see, like, let's check it. Let's check this. Since there are three vertices, let's check for this. So first we have to check for A. Is conservation law satisfied for A or not? So you see, so we have to first check the flow out of A. So you see there are three edges which are attached to A. Two edges are coming into A, SA and BA. And there's just one edge which is going out of A, which is AT. And 2 is equal to 1 plus 1. So flow value, in this slash value, this is the flow value and this is the capacity. So you can see 2 is equal to 1 plus 1. Therefore, conservation law is satisfied for A. And similarly for B. Now if we look at B, there are two edges going out of B, which are BA and BC, and there is just one edge which is coming into B, which is SB. And flow values also are satisfying the equality, that FBC plus FBA should equal to FSB. And for C vertex, there's just one edge coming into E and there's just one edge going out of C. So, and both have flow value 1. So it is also satisfied for this. So we see capacity rule and conservation law is satisfied for this for this flow. Therefore, we see that this is indeed a flow. So did everyone understand what is a flow, or is there any confusion among any of the two rules? That is the conservation law and the capacity rule. Is everyone
Clear,
can change
ma'am.
the flow value also.
sorry? Yeah.
You can change the flow value, no?
Yes,
It is
yes,
a
we can.
message that the
Yes.
flow value should be as per your what you have written.
No.
It
This is
can be
just,
changed. No?
yes. This is just one example depicting that this is indeed a flow. This is an example. We were just checking that given this function, are both the rules satisfied or not? And
Okay.
if both the rules are satisfied, this is a flow. Okay. So now once we understand what's a flow, then there's to each flow, that flow we have seen, it is a function which is assigning some non-negative real number to to each of the edges. Now we also have a value assigned to flow, which we call total flow or value of flow. And what is the value of flow? Value of flow is basically either we compute flow out of source or flow into sink. So what do I mean by flow out of source? Basically we are summing up flow values over the edges which are going out of S. Or we are or in a, there's another way to compute value of flow, that is we compute flow into the sink vertex. So T is a sink vertex. We can either we can either take add or flow over the edges coming into T. So these, and due to conservation law, both these quantities are same, hence we can calculate flow with any of these quantity. So in this particular example, we can see what is the flow. So there are two ways. So this is the source vertex, so we are computing flow going out of S. So this is 1 plus 2 3. So flow for so the total value of flow for this flow is 3. And you can check for if we computed it using the sink vertex, then also it is coming out to be 3, because there are two edges which are coming into T, namely AT and CT, and if we add up, they are coming out to be 3. So this is the total value of flow. So let's just do one question on the basic definition of flow that we have done up till now. So this is question from one of the this is the question from the from week 7 assignment only. So what is the question? So we are given this is the network. On left hand side we have a network, but it is an incomplete network because we don't have any direction attached to any of the edge. So now our task is to so this is network, and also we have also been provided with the flow values. So there are two integers attached to each of the edge. This So this first integer is your flow value, and the second integer is your capacity. Now our aim, our the question is asking us to the question is asking us to give directions in this graph so that the conservation law is satisfied. So I've just discussed what the conservation law is. Other than source and sink vertex, all the other than the source and sink vertex, we should we make sure that flow coming into some vertex should be equal to flow going out of the vertex. So let's do this question. So first of all, so this is the source vertex, and we are given that flow is 23. So if our flow is 23, can we immediately give directions to some of the edges? We are given that flow value is 23. So what is flow value? Flow value is basically the flow value for all the flow which is going out of S. So can we give some directions? We are given that flow is 23.
Yes, ma'am.
Yeah.
From source we can give, ma'am, from S to A, S to E, and S to H.
Yes, good. So S to A, this is the direction, S to E is the direction, and S to H is the direction. Right. So now we see if the flow value is 23, 8 plus 3, 11 plus 12 is coming out to be 23. So this is satisfied. So we see this is indeed correct. These three directions are indeed correct. Now I want to check conservation law at vertex H. So we see that there are three edges, FSH, FEH, and FHI. So we are, and SH has wait SH has flow value 12, EH has flow value 4, and HI has flow value 8. So what do you think should be the directions for these edges?
H to E, H to I, ma'am.
H to E and H to I, because 12 flow value of 12 is coming into H. So as per conservation law, flow there should be flow 12 which is also going out of H. Hence he is correct. So the direction should be H E and H I. Yes, good. So these are the directions for H I. Now what about F I and I J?
IF and IJ.
From I, it moves to F.
IF and
Yes.
IJ.
Yeah,
And I to J and I to F.
uh, I to F, yes, and
And I
I
to
And
J.
I
I
to
to
J.
J. Yes, very good. Yes, this is also correct. Now, okay. So now what should we do? Now, what about the vertex J? What about these edges GJ and JT? What should be the
G
direction?
G to J and J to C.
J
G
to
to J
yes.
G to J.
Uh, okay. Yes, G to J and
and
J
J to T.
to T. So here also satisfy the conservation law. So six, coming into is Fij plus Fgj should be equal to Fjt, which is 6 plus 1 should equal to 7. So these correct directions are also correct. So now what about Ct and Gt
C to T
and G
and
to
G to T.
because
Think.
yes, T is a sync vertex, so these should these should go into T. And so now what we are left with few more edges. So then we have FG and CG.
F to G and
Yes.
C to G.
Yeah. So see, yeah. So since CG has value 0, we can give either of the direction. It doesn't matter. Like we can either give CG or GC. It won't matter because CG has value 0. So it is not contributing to flow at either side. So any of the direction will be fine. And now we have few more edges. So we have like, okay. So what about BF and EF? What direction should be for BF and EF?
E to F and F to B.
Okay, so if we are doing E to F, then the flow into F is 10 plus 2, 12. And now if we are doing B to F, then
No, F
flow
to B, I
out
think.
F to B,
F
ma'am.
to B,
Yeah, F
yeah,
to
F
B,
to
F
B.
to B.
F to B, yeah. Because flow out of F should also be 12. So F to B and F to G, 7 plus 5, 12. Okay, good. Now we have three more edges left, AE, AB and BC. So what should be the directions for these?
A to E,
A to B, you're saying?
E. A to B and A to E.
A to B and A to E. Yes, this is
Ah,
correct
I
because
to C. What I to C is A.
inflow is A. Good, very good. And now for BC, what should be the direction?
B to C.
B to C.
B to C. Yes. Okay. So this was our first question. So I think everyone, so we have given directions to each of the edges. So I think there's no confusion in this. So if you have any confusion in first question, you can ask. Okay. Okay. So now let's move on to more concepts. Okay. So now we have done what we have seen what is a flow. Now once we have there's a concept of maximum flow. Now there's also a concept of minimum cut. So let's see what is this minimum cut. First of all, what is a cut? So we have discussed cut in various lecture. So cut is basically something which is it is a disjoint union of two set S union S bar, and this is partitioning V. That means S union S bar is equal to V, and edges in this cut basically refers to the edges in which whose one endpoint is in S and other endpoint is in S bar. And once we have defined what is a cut, what is an ST cut? By ST cut we means a cut where source vertex, that is S, is belonging to S, and the sink vertex, which is T, is belonging to S complement or S bar. So we see this is an ST. This is the definition of ST cut. So now once we have a ST cut, then we can attach two numbers to it. First is the capacity of a cut and other is the net flow of a cut. So what is the capacity of cut? So capacity of cut is basically, which we are denoting by CSS bar, is we are adding up all the capacities which are summing over edges whose first vertex these are a direct, UV is a directed edge whose first vertex is in S and the second vertex is in S bar. So if in this graph G, in this network G, if I am taking my cut as ABS, so I have drawn this line, so this is the cut. These three vertices SAB are belonging to S and CDT are in S bar. So what is the capacity of cut? We have to add up the capacity of all the edges whose one vertex is in S and the other vertex is in S bar. So in this graph you can see there are just two such edges, AC and BD. So the capacity of cut will be capacity of AC plus capacity of BD, which is 4 plus 3, 7. And so this is the capacity of cut. And now what is the net flow of cut? Net flow of cut is basically the difference between, so first we compute flow out of S. So flow out of S we mean flow values, and we are summing up all those edges whose we are summing up all those edges whose vertex are coming into S, and then we are subtracting the flow values from all those edges so we are summing up flow out of S. So basically flow going out of S minus flow into S, so flow coming into S. So if you look at this cut has three vertices ABS. So what will be flow out of S? Flow out of little s vertex. So there are two edges which are going out of S, namely SA and SB. So if we want to compute the net flow, it is FSA plus FSB. Then we look for the other vertex, which is A. So we see there is one edge which is going out of A, which is AC, and there are two edges which are coming into A. So we'll subtract those flow values, FAC minus FSA minus FBA. And then the third vertex is B. So we see there are two edges which are going out of B, which is BD and BA. So we sum up BD and BA and we subtract the flow coming into B through S, which is SB. So now we see, like if we look at these calculation, FSA, SA will cut down, FSB could cut down, FBA will cut down, and we are just left with flow value of AC and flow value of BD. So which is 3 plus 2, 5. So net flow of cut is this. And also you can see, so when we are computing net flow, so some of these flows values are being cut. So what flow values are remaining? Only those flow values are remaining whose one vertex is in S and other vertex is in S bar. So so basically when we are computing net flow of a cut, what we are doing, first we are adding flow out of S. So we are adding all the flow values from the edges whose edges going out of S, and we are subtracting the flow values of edges coming into S. But many cancellations are happening, and after cancellation only those edges are remaining which are the edges of cut, that is whose one vertex is in S and other vertex is in S bar. And so this is the net flow of cut. And once we have defined what is the capacity of cut and net flow of cut, we have three preliminary lemmas which shows some relation. So we can see that net flow of any cut will always be equal to the value of total flow. Lemma 2 is value of total flow will always be less than equal to the capacity of cut. And thirdly is if we have any cut whose capacity is coming out to be equal to the flow, then due to this lemma 2 is applicable for any flow value or any cut. So we can see that if flow is coming out to be equal to capacity of some cut, then that flow value is the maximum flow value, and that cut is the minimum cut. So what do we mean by minimum cut? Cut whose capacity cut with minimum capacity. So in this example, you can see all these first two equalities are being satisfied. So first of all, what is the flow value in this graph? So in this directed graph, what is the total flow? Who will tell? Somebody tell. What is the flow value in this network? We have just seen what is the flow. Flow is basically either we compute all the flow values going out of the source vertex, or all the flow values going into the sink vertex. So what is the flow value for this network?
5.
5.
5.
Yes. So the flow value is 5. This was 3 plus 2. And we see the first all these first lemma is satisfied. That is first lemma is satisfied, which is flow value should equal to the net flow of cut. So net flow of cut is also coming out to be 5, and flow value is also coming out to be 5. So we see that first lemma is satisfied for this example. But this lemma claims that this is true for any cut and any flow. And second lemma was that the net flow value should be less than equal to the capacity. So here we can see the capacity is 7 and flow is 5, and 5 is less than equal to 7. So second thing is also satisfied. And the third thing lemma is this, that if flow is equal to the capacity of some cut, then that cut will be minimum and flow will be maximum. Okay. So now let's look at some examples for computing capacity and flow. So we have this directed network Chi, and my cut is SB. So SB is SB. So we have in S we have SB, and in the S complement we have ATC. So what is the capacity? Capacity is basically we have to sum up the capacity of all those edges whose first vertex is in S and the second vertex is in S bar. And also in this and we can see in this cut, S is belonging to S, little s is belonging to S, and T is belonging to S bar. So this is a ST cut. So now what is the capacity of this cut? So we can see there are just 3 such edges whose one vertex is in S, and the other vertex is in T bar, which is SA, BA and BC. So for capacity we see 2 plus 1 plus 1, which is coming out to be 4. And for flow value also we have to compute flow over these vertex. So we flow over these all those edges whose one vertex is in S and other vertex is in S bar. So we see it is the flow value is 1 1 1 for each. So we see flow value is 3, and here we see that the flow of S bar is less than equal to CS bar capacity. Therefore we cannot say that this is the maximum flow. But in the next example, will see that capacity is coming out to be equal to be flow. So from lemma 3, this is the maximum flow. This is maximum flow. So for lemma, for B part, what is our cut? It is first SAB, and the other vertices are T and C. So we see there are 2 such edges, AC and BC. So we are looking, AT and BC. So capacity is 3 and flow is also 3. So we see flow is coming out to be capacity. So this is indeed this. Since flow of this cut is coming out to be the capacity of the cut, from lemma 3 we can conclude that flow value of 3 is maximum, and this SS bar this cut is the minimum cut. So is the concept of uh, capacity of cut and flow clear to everybody? Can we move on to questions, or if you have some doubts in this, then we can discuss that. Yeah. Yes.
Ma'am, once again explain about minimum cut, ma'am.
Okay. So by minimum cut, what we mean? So, okay. So first of all, definition I haven't defined of minimum cut. It is basically, minimum cut is basically, so we know what is a cut. Cut is basically disjoint union of two set S and S complement whose union is V. And minimum. So if we consider all such cuts, and if we find out, if we consider all such possible cuts, and if we find out the capacity of all such cut, the cut with the minimum capacity value. So among all those cuts, the cut having minimum capacity, the least capacity will be your minimum cut. Now from lemma 3, so we have these three lemmas. So first is that flow value always come out to be equal to the net flow of any cut. Then second is net flow value should be less than equal to some capacity. Flow should be less than equal to capacity of any cut. And third lemma is saying that if due to this lemma 2, so we have this lemma that if we take any flow and any capacity, this equality, this is, we have this inequality. So if flow comes, so if we can find some flow whose flow, if we can find a cut whose capacity is coming equal to flow, from this lemma we know that this F will be the maximum flow and this cut will be minimum. So in this example we are seeing that flow value is 3, flow value is 3, and capacity is also 3. So lemma 3, hypothesis of lemma 3 is satisfied, that capacity is equal to the flow. And if such thing happens, then this cut is the minimum cut. That is, if you will take any cut and if you will compute capacity of that cut, that capacity of any cut will be greater than equal to 3. It cannot be less than 3. Therefore this is the minimum cut. So is it clear now?
Madam, what is mean by total flow? Is total flow is equal to maximum flow? There is no concept of total flow in this flow chart, network.
Total flow is just the value of flow. By total flow is just value of flow. That is this value that we are computing.
Which one?
This value, that is the flow going out of source vertex or flow coming into sink vertex. So this,
So is flow coming into the same? Is it maximum flow or
no,
total
no,
flow?
this is so flow value, basically flow, the function f, the value of that flow. So it need not be maximum. it it need not be maximum. By maximum flow we means we can, so we have this, what is a flow? Flow is basically a function which is assigning a non-negative value to each s such that two rules are satisfied: conservation law and capacity rule. And if we consider all such functions, uh, if we consider all such functions which are possible, all the possible flow functions, the function which will have the maximum flow is the maximum flow. Maximum flow is the flow with maximum total flow. So this is just, so when we are assigning these integers, this is just one example of a flow. So when we are referring to total flow, we are just saying the, when I am referring to total flow, I mean that the value of flow for this for this particular function flow, for this particular f. But it need not be maximum. We'll see later. So we, the next concept is that only. So how to find the maximum flow? Give but it need, so this is just one example of a flow.
Mean you are taken cut at maximum capacity or at maximum flow.
Okay,
But
yes.
at
Yes. So see, in this example, in this example, since this lemma is satisfied that capacity is coming out to be flow, so in this example this particular flow is also the maximum flow. By that we mean, if we consider and if we construct any such function, any other f prime, say any other g prime which is satisfying conservation law as well as capacity rule, and if we compute the total value of g, that is value of g, that value will be less than equal to 3. So in this example, from lemma 3 we can conclude that since the capacity of this cut is coming out to be equal to the net flow, since capacity of this cut is coming out to be equal to net flow, this is the maximum flow. That is, this is a function whose value is maximum. Value of flow is maximum. Do you,
And this cut is the minimum cut.
yes, this cut is the minimum cut. From lemma 3 we are concluding that.
Okay, ma'am. For that, the flow and the capacity value should be equal.
Yes, if the capacity of cut is coming out to be flow, net flow of some cut, then lemma 3 says that that cut will be minimum. That cut will be minimum basically means that if we consider any other cut and if we calculate the capacity of that cut, the capacity of some other cut will always be greater than equal to the capacity of minimum cut. And this will also be the maximum flow. So what do we mean by maximum flow? If we consider any other function g which is satisfying the conservation law and the capacity rule, and if we compute the flow value for that g, flow value will come out to be less than equal to f, because this flow value is maximum from lemma 3.
And
So
that means if the capacity of the cut is maximum, is it maximum flow?
no, yes, if the capacity of cut is minimum, then the flow is maximum.
Okay.
Lemma 3, this is the, we'll see this is the max flow min cut theorem, right? So if we want to find finding maximum flow is same as finding the minimum cut. So due to this inequality, so lemma 2 says that flow is always less than so if we consider any function f which is satisfying those two conditions, conservation law and capacity rule, and if we take any cut, then flow of any function will be less than equal to capacity of any function. So if this capacity is minimum, then flow is maximum, and if flow is maximum, capacity is minimum. Capacity of cut is minimum. Okay, so we'll
So ma'am,
see. Yeah.
is there any method? Is there any method to
To
find out the minimum cut without going for that this thing?
okay. Yes. Uh uh so
You
if you
finding
so
out
minimum, see, so we'll be
residual graph and
we'll
then augmented graph.
yes, we'll be discussing a method to find the maximum flow, and through that maximum flow we can find the minimum cut. But I'm not aware if we aware of any method in which we can find the minimum cut directly like,
No, that is the yeah.
yeah,
Because
sorry.
it is time consuming. No, it is a time consuming to find out the maximum flow
Hmm.
by that full person method of this thing
Yes.
algorithm.
Yes. Yes,
It is a time consuming. So
but I think if there is any
there
algorithm
is a
for, hmm, yeah, but if you are trying to,
directly
hmm,
if you can find out
mm,
directly if you can find out the
hmm,
minimum cut,
hmm.
then there is no need to go for that algorithm.
But I think, like, okay, I am not aware of any
Find out
algorithm,
the
but
thing.
if we are trying to find minimum cut also, I think that algorithm will also be time consuming. So there is no direct way, because there is no direct way to find such things. So that like, I think there might be some efficient algorithms, but they'll take
Hmm.
some time. Or like, see, or you can see, like, you can try some random, like, but that is also random thing. See, this like, if you find take some cut, try to find its capacity, try to find its flow, and if they are coming out to be equal, like in this, I just picked up some random cut and they turned out to be equal. So then I don't have to perform this algorithm. From the lemma 3, I can directly conclude that this is minimum cut and this is the maximum capacity. But this is an hit and trial method. So this is not any method, right? It's just, so yeah, I'm not,
Ma'am, one more doubt, ma'am.
yes, yeah.
If we find the maximum flow value, uh, then we can conclude that same value will be for minimum cut.
Yes, yeah,
So
yes. Hmm.
so if we have any four minimum cuts, we can calculate the capacity value, and which value is coming equal to the maximum flow, we can conclude that that is the minimum cut.
Yes, 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 you are correct. Yes,
Okay, okay, ma'am. Okay.
yes. Okay. So now let's do some questions. So this is also from your assignment. So this is what this we have done in first question. So we were given some network, we were given, and we gave the direction. So first question is this: we are given a cut and we have to find the net flow, find capacity and net flow. So let's do this. So we have this cut. We have this cut. S has the, oh, sorry, this is the cut. So see, this cut is partitioning the vertices. So first set has these many vertices which are circled with blue: S, A, E, F, H, I, J. And the second set, S complement, is the leftover vertices which are B, C, G, T. Now this first question is saying, question 2 is saying basically to find the capacity. So what is the capacity of this cut? So who will tell? Somebody tell. So capacity is basically, we have to sum capacity over all the edges whose first vertex is in S and the second vertex is in S bar. So what all edges should we consider?
A to
A,
E,
B,
A
A
A
to
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 B,
B.
B,
Okay, yeah.
A to B, F to G,
A
A,
to
B, A
G
to
B.
B,
to J,
Oh,
and
A
J
to
okay.
to
B, F to B,
Okay, one by one. First is A to B. Okay. Second,
F,
okay.
F to B,
F
yes.
to G, F to G.
F
F
to
to
Oh
G,
B.
yeah,
F to
yeah. F to
B.
B,
F,
F to
F to
G.
G,
Yes. Then
G to
and
J,
J to T,
G to T.
J to T, J to
J
T.
to T.
Yes, so somebody said G to J. So will we add G to J or not?
No,
No, ma'am, actually it is an S form.
it will not
Yes,
be.
yes,
Because
yes.
it is other way.
Yeah, yes. So okay, so this was mistake, but this is an important mistake. So see, like we have to consider capacity of all those edges. So we can see that G, one vertex of this GJ edge is lying in S and other in S bar. But what is the other condition? First vertex, but first vertex is in S bar. So we don't compute the capacity, or we don't take the capacity, add the capacity for this. So what? So now we have to consider all these edges. So what is the capacity value? CAB plus CBF plus CFG and plus CGT. So we see
JT,
GT, yeah. So now
JT.
this is G.
Okay.
This is G.
JT, no?
Huh. So I said GT, right?
JT.
Huh. I said GT. Yeah. CAB is 5.
Five,
So this is FB, sorry. This is FB. FB. CFB. This is also 5. This is 7. And
7
G.
and 7. 7.
Oh, the GT is not there. Sorry. You're right. Okay, sorry.
JT, no. JT, JT.
G. Oh, yeah. Okay, now I understand what you were saying. Sorry. GT. It should be JT. Yeah. JT. JT. And this is also 7, and if we add this up, this is coming out to be 24. Now okay, so we see we have done this. So now how do we find the net flow? So who will tell the net flow? So basically, see, this is what I told you. So when we are computing net flow, what we have to compute? We have to compute flow into, we have to compute, add all the flow going out of S and subtract all the flow into S. But we see when we write down all those things, all the edges got cancelled, all the capacities got cancelled, other than the edges whose one vertex is in S and other vertex is in S bar. So we see there are four such edges, and there's also this fifth edge, GJ.
GJ, S bar
JJ.
to S.
Yes, this is S
That
bar.
is
So when we are computing capacity, we don't worry about any edge from S bar to S. But when we are computing net flow, we have to worry about both the edges. That is the edges from S to S bar and edges from S bar to S. So we are adding. So when we are computing net flow, we have to add all the flow of edges from S to S bar and subtract the flow from edges from S bar to S. So we see that we have to these so if we want to compute net flow, we have to worry about only the flow values of these five edges. All the other values will get cancelled. So now what is the net flow? So what among all these five edges, what all four quantities should be added and one quantity should be subtracted? So what all quantities should be added and what all should be subtracted? So first of all, did everyone understand why we
5
have?
plus 5 plus
Yes. Okay. First of all, did
9.
everyone understand why we have to worry about only these five edges and not the rest of the edges? So I am saying that flow of yeah. So is it clear to everybody why we have to just worry about these five edges and not the other edges? Okay. So see, I'm just so if we so basically when we are computing net flow, what we are doing, we have to add flow in out
Yes,
of
yes.
flow
It's a
out.
cut.
Correct.
Okay.
So see, huh? So you see, like if we look at this edge EF, if we look at this edge EF, so when we will be computing net flow, we'll be adding FEF because it is going out of E, which is in S. But we'll also be subtracting it because the other vertex is also lying in S. So this quantity for any if any two vertices are lying in S or S bar, both those quantities are getting so both those quantities are getting cancelled. So we see we just have to worry about the edges whose one vertex is in S and other vertex is in S bar. So now if we want to compute flow of this, so what is the flow of this cut?
5.
Can you tell the edge
5 plus
also?
5.
Can you tell the edge also?
AB.
Yes.
A
FAB
to
plus,
B.
yes, plus
B to C. B
B
to
to
F.
F to B.
F.
F to
F
B.
to B.
F to B. This is the direction.
F to B. Yeah.
Yeah. Plus
F to G.
F to
F
G.
to G. Yes.
J to T.
J to T. And we subtract
Minus.
Minus
J to
G
J.
to
G
F.
to J.
G minus G to J. Yes.
G to J. Minus G
G
to
to
J.
J.
Because it is in the other direction, it is going from S bar to S, so we'll
S bar to
subtract
S.
this. So now if we add up these value, we'll see that it is 5, this is also 5, this is 7,
7.
this is 7, and this is 1.
1.
So this is 24 minus 1, which is 23.
23.
Okay, so is this question clear to everybody? Net flow and capacity. So given a cut, we have to find the capacity and net flow. So is it clear with everybody?
Yes.
Okay. Yes. Is there any question?
Yes, ma'am.
Yeah. Okay. Okay. Now once we have done this, now we have defined what is the maximum flow. We have looked at what is the minimum cut. Now we are trying to look for some methods to given a network to compute maximum flow or the minimum cut. So for this we have to introduce two more concepts. First is given a network and then given a flow, we'll first construct a residual flow. So what is residual flow? So we are given a network G and we are also given a flow F. So residual flow is also a directed graph and whose vertices or edges are as follows. So vertices are same as the vertices of G and edges. So we see that in G we have some edges. So for each edge in G, we either construct one edge or two edge in the residual flow with respect to these rules. So capacity rule says that flow value will always be less than equal to the capacity. Capacity rule says this. So but if we have so first we are looking at this directed edge uv which is in this direction. So if the flow value is strictly less than the capacity value, then we will in the residual flow diagram we'll draw an edge with direction uv whose capacity, whose now the new capacity will be the difference of these two values, that is capacity minus flow. And secondly, if we have flow value which if we have flow which value which is strictly greater than 0, then we'll also draw an edge in the reverse direction fvu. So uv there was an edge in the direction of uv. We'll draw it in reverse direction vu whose now the new capacity will be and the capacity of this edge will be equal to the flow value. So we have these two rules to compute the residual flow, and we see that since we have these two conditions, so we can either draw one edge or two edge. If both these conditions are satisfied, for each edge uv we'll have two edges. If only one of these condition is satisfied, then we'll have one edge. So now this is an example of how to construct the residual flow. So this is my network G and this is my flow. So if we have this 3 by 4, so 3 is giving me the flow value and 4 is giving me the capacity value. So now let's draw this. Let's do it for SA first. So first of all we see that FSA is 3, which is strictly less than the capacity value, which is 5. So rule A is satisfied. Therefore, we will have a edge in the same direction, which is SA, with flow value 2, which is the difference. And also we see for SA, the capacity value is strictly greater than 0. It is 3. Therefore, we'll also have an edge in the opposite direction, that is in the direction AS with the capacity 3. So this was for AS. Now let's look at for the edge CT. Now for edge CT we see that flow of CT is equal to the capacity of CT. So the first condition is not satisfied. So there won't be an edge in the direction of CT in the residual graph because the first condition is not satisfied. But the capacity of CT is 2, which is strictly greater than 0. Second condition is satisfied. So we will have an edge in the opposite direction, which is TC with the capacity with the new capacity 2 because the flow value was 2. And now let's look at some other case also. Suppose we have this case of AB, edge AB. Now for this edge AB we see that flow value is 0, which is strictly less than the capacity value. Therefore we will have an edge in the direction BA. Sorry, this was edge BA. Therefore we will have In the residual flow diagram, therefore we will have an edge in the direction BA with the capacity which is the difference 3 minus 0 3. But capacity of BA is 0. So second condition is not satisfied. So we won't have any edge in the reverse direction. And you can see for rest of these edges other than these three edges, all other both the conditions are satisfied. So we have one edge going in the same direction and other edge is going in the different other opposite direction, and the edge going in the same direction has capacity which is the difference of flow and capacity, and the edge in the reverse direction has capacity equal to the flow value. So did everyone understand given a flow and network how to construct a residual flow?
Hmm.
Yes, ma'am.
Okay. Okay. So now once we have done what is residual flow, the next is, once we have done what is the residual flow, now given a flow and given a network, we have a residual flow graph attached to it. And after residual flow, we talk about augmenting path. So what is an augmenting path? Augmenting path is a path which is starting at source vertex, ending at T vertex in the residual flow graph. So in this example, you can see this was the residual flow diagram. SA, SA, AC, CD, and DT. This is a path from S to T in the residual flow diagram. So this is an augmenting path. So this is what we mean by augmenting path. So do you think there is any other augmenting path in this? So this is one example of an augmenting path. Is there any other augmenting path in this residual flow diagram? Can you give me another example of residue
Yes, ma'am.
augmenting
We can
path?
take
Yes, we can take
we, we can take SA,
SAACCA. Okay.
AS, AS,
Wait. Okay.
SV,
SAACCA.
CA,
Okay.
AS,
AS.
SB,
SB.
SB,
Sorry, after SB what?
BD,
BD.
BD,
Yes, BD. Yes.
and DT,
DT.
DT,
BD, DT. Yeah. But see,
DT.
DT, right?
Hmm.
But see, this is not a path because S is getting repeated. So up in a path, no. So your path is basically SACSBDT, right? But S is getting repeated in this. And in a path is basically in path no vertex should be repeated. So this is not a path.
Okay.
But you can give, using this path you can give me a path, right? Your example was partially correct.
Another path is path is SBBD
Yes. So see, this is the path SBDT.
BD and DT.
DT. So in this, see, we can see no vertex is getting repeated, and it is a path going from S to T. So this is another example. So the other example is of augmenting path is SB, BD, and DT. Or okay, sorry, we can write it like this: S, B, D, T. Okay. So that, does everyone understand what is an augmenting path and why the previous example, previous suggestion that SACSBDT, this was not a path because S was getting repeated. So but this is a path, SBDT and SACDT. So does everyone understand what is an augmenting path?
Yes, ma'am.
Okay. Now, once we have augmenting path, we can talk about the path capacity. Path capacity is basically path capacity is basically we look at the capacity of all the edges. Yes.
नहीं मेरा लीक नहीं है.
Sorry, is there a question? Hello. Okay. So okay, so what is the path capacity? Path capacity is basically we look at the capacity of all the edges appearing in the augmenting path, and the uh, and the minimum of those capacity is the path capacity. So there are two augmenting paths in the previous question, in the previous example. Once first path is SA AC CD DT. So and the capacities are 2115, and we see the minimum of 2115 is 1. Therefore for this path the path capacity is 1. But what about the path capacity of the other path, which is SBDT? What is the path capacity for this path?
215. Minimum of 215.
Yes, minimum of SB has, which is capacity 2,
2,
BD which has capacity
2,
1,
1 and 5.
5. So minimum is 1. So we can see that this path also has capacity 1. And now, so now the now we have, so we see that if we have if we have an augmenting path with a if we have an augmenting path and path capacity, we can construct a flow. That is, we can construct a new function with a new function which is satisfying the conservation law as well as the capacity rule, but which has higher flow value. So in this the flow value was 5. In this the flow value was 5. So now how we construct the new flow? How do we construct the new flow? Basically we had this augmenting path. Okay, so we had this augmenting path. First path was SACDT. So we had this augmenting path and path capacity was 1. So in this augmenting path they are all in the same direction. So if you want to construct a new flow, what we do in this augmenting path, we change it with the path capacity. So path capacity was 1. So the new flow in this will have 4, 3 plus 1. This will also have 3 plus 1, which is 4, because the direction is also same. So we have this path SAACDT. So in this path we see SA is in the same direction as in G, and AC is also in the same direction, CD is also in the same direction, DT is also in the same direction. So we will add 1 to each of the flow value. So our new flow will be this will be 2 and this will be 4. So this is our new flow. And now you see, so this is our new flow F prime. And now in this flow, if we compute the flow value, this is coming out to be 4 plus 2, 6, which is greater than flow value of the previous pre- flow value of previous graph 1. So we see that if we sorry. So we see that if we have a flow and if we have an augmenting path in a residual flow, then we can construct a new flow we can construct a new flow which has higher value, like we have constructed in this example. So does everyone understand that if we are first of all there are three steps here. So first we were given a flow, then using that flow we constructed a residual flow diagram. After constructing residual flow diagram, we look for an augmenting path. Augmenting path was a path from S to T, and S to T in the residual flow diagram. And once we have the once we have the augmenting path, we looked at the path capacity. Path capacity, it was the minimum of those value, and after getting path capacity along those path edges, we are changing our flow values to get a new flow. And the rule is basic. So sadly in this example, all the path in this path, augmenting path, all the paths are in the same direction. That is, there is no red edge with the red direction. So when we are constructing new flow, we are adding path capacity to each of the existing flow, and in this manner we are able to get a new flow diagram. And you can check that this new function is also satisfying the conservation law and the capacity rule. So this is indeed a flow function. So does everyone understand this process? That given, if we have some augmenting paths, how can, if we have some augmenting path in a residual flow diagram, how can we construct a new flow which has a higher value?
Yes, ma'am.
Yes.
Ma'am, one doubt, ma'am.
Yes, your doubt.
Uh, Whether the augmenting path should have both the forward edges and backward edges.
As in, so see, yeah, so augmenting path is basically any path from S to T. So it is not necessary that all the edges should be forward or all the edges should be backward. All edges are allowed. And all edges are allowed, but we should not repeat any vertex. We should not repeat any vertex. We are just
Okay.
looking for. So in this example, sad like in this example, we are getting path which has all the forward edges, but it's not necessary that we'll always get that. We'll see in later examples. So now when we are constructing new flow, so we are to all those forward edges we add the path capacity, and to all the forward edges appearing in the path we add the path capacity, and to all the backward edges appearing in that path we subtract the path capacity. And we see that will new, so we construct a new flow in that manner. So now is it clear?
Yes, yes, ma'am. Yes, ma'am.
Okay, so now we see that okay, so this is also this is also the residue flow for f prime. Now this is residual flow for f prime. So now do we have any augmenting path in this diagram, in this new, in the residue flow for f prime?
Yes, it is.
Yeah. Yes.
Speaking. No.
We have like the previous one only, SBBD and DT.
SBDT and
DT, right?
yes, ma'am.
SBBD and DT. So this we have an augmenting path here also. So now once we have an augmenting path here, so that means that if we have an augmenting path, we can construct a new flow. We can construct a new flow function with a higher flow value. So now what will be the new flow value? So this is our f prime. Now what will be the new flow values if we are looking at this path SBT BTT? So this is our path Q. So what is the
V flow.
capacity of Q? What is the capacity of Q?
Capacity of
Capacity of this path Q, which is SBDT.
it is one.
It is 1. Yes. Because
1.
yes, because minimum value is minimum of 2,
1.
1, 4, 1. And what we have to do to find the new flow, what we have to now, if we want to make construct new flow, what do we do?
SB become 3 by 4.
Yes.
S to B.
Yes, so here also we see, but here in this example also we are getting all those forward edges. So we are just we'll just add path capacity to each of them. So this will be 3 out of 4, this will be 3 out of 3, and this will be 5 out of 8. And now the new flow value will be 7. 5 plus 2, 7. So we see that this f prime was also not the maximum flow because there was an augmenting path in the residue flow diagram. So from these example we can observe that if we have an augmenting path in a residue flow diagram, then we can always construct a new flow which has a higher flow value. Therefore, if we have any augmenting path in residue flow diagram, that flow cannot be maximum, and we exploit this observation to find the maximum flow. So if we are given some network, if we are given some network G, if we are given some network G, and if we want to find the maximum flow, what are the steps to find the maximum flow? Initially we set all the flow values to be 0. So if we set all the flow values to be 0, this is a valid flow function, because all those two, the capacity rule is also satisfied, capacity rule is also satisfied, and the conservation law is also satisfied, because flow in coming into any vertex is 0 and flow going out of any vertex other than ST is 0. So this is a valid flow. Now given this initial trivial flow, what we do, we construct the residue flow diagram. After constructing residual flow diagram, we look for an augmenting path, and as the previous example, once we have an augmenting path, we construct the new flow as this rule. So what will be the new flow? So if in this path uv, if in the augmenting path q, uv is a forward direction, uv is an edge in forward direction, we add the path capacity. But if uv is in the reverse direction, we subtract the path capacity, and using that rule we get our new flow. And we keep on doing this, we keep repeating this process, that is getting a flow, constructing a residue flow diagram, then constructing the augmenting path, using the augmenting path to construct a new flow. We keep on doing this until we reach a stage, we get a flow where there are no augmenting paths. And when we reach that stage, when we have no augmenting path, we claim that will be our maximum flow. So this is the augmenting path algorithm to find the maximum flow. So is the algorithm clear to everybody what we are doing?
Yes, ma'am.
Okay.
So, ma'am, one doubt,
Yes,
ma'am.
yes, yeah.
So, to find the maximum flow, we have to find first the residual network and the augmenting path.
Yes, yes.
Okay, ma'am. Okay.
And we keep on doing it until we reach a flow which has no augmenting path.
Okay, ma'am. Okay.
Yes. Okay. Now let's do some questions. Or okay. So there is one more. So this is the last result of today's. This is the result that if we are given a network, then these three conditions are equivalent. That is, f is the maximum flow, there is no augmenting path in the residual flow of f, and thirdly that we have a cut with the net flow value. So in the previous algorithm, what did we see? In the previous algorithm, we saw that if we are given any network, we can construct the maximum flow. Now we are looking at the other way direction, that once we have a maximum flow, how do we construct a minimum cut? let's look at this with an example. So now our next problem is, if we are given a maximum flow, how can we find the minimum cut? Because we know that maximum flow equals value of maximum flow equals the value of minimum cut. So if we can find, if given any maximum flow, we can find a minimum cut will be, this will be done. So this is an example. So this is our network, and these are the flow values. And so we see the flow value in this network is 3. So if we look 1, 2, so if we are looking at the flow value coming out of S is 3, and flow value coming into T is also 3. So this is the flow value. Now this is the residual flow diagram for this flow value. So the the pink edges are the edges in backward direction. So this you can see that this residual flow diagram has no augmenting path. So is everyone convinced? Like, can you find an augmenting path in this residual flow diagram? So this is the flow and this is the residual flow. Do you this I am saying that there is no augmenting path.
No.
No. Okay. Is everyone convinced that there is no augmenting path? So to find a augmenting path, we want to find a path from S to T. But we see that there is no path from S to T, because there are two ways. Either we can go to S to B, but there is no edge going out of B, so we cannot go to any other place. And here also from S to A there is no edge going, so S to A, then A to B, but then also we are stuck. So we see that this residual flow diagram has no augmenting path. And so from previous algorithm, we know that this is indeed the maximum flow. Now we are given that this is the maximum flow. We want to find the minimum cut. So how do we find the minimum cut? So this maximum flow has flow value 3. So minimum cut is basically set of, so what is our S for the minimum ST cut? The minimum, so S is the set of all vertices U such that there is a path from S to U in residual flow diagram. So in this example, so what are the vertices such that there is a path from S to that vertex? So what is there a path from S to A in residual flow? Is there a path from S to A?
Yes,
Yes.
ma'am.
Yes. And is there a path from S to B?
Yes, ma'am.
Yes. Yes.
Is there a path from S to C?
Yes. No.
No,
No.
ma'am. No.
And is there a path from S to T?
No, ma'am.
No.
No.
So we are saying that if we consider this as our S, then this will give us the minimum cut. So is this happening? So what is the capacity of this cut? So this is our cut. So this is our cut SABCT. So what are the edges? Oh, sorry, this not in cut we consider in the initial network, not in the residual flow. So this is the cut. So what are the edges? So this is the cut S, B, A in one, and CT in the other set. So what all edges are there from S to S bar? AT
A
and
to A to T. A
A
to
to
T
T
and B
and B
to
to
C.
C. And this is coming, and so the capacity is coming out to be 3, which is equal to the flow value. So from our lemma 3 we can conclude that and so if capacity is this, and we already know that from lemma 2 that net flow always come out to be the flow value. So from our lemma 3 we can conclude that this is indeed the minimum cut. So given a maximum flow, what is the procedure to find minimum cut?
And,
Yes,
and
yes.
can we take a cut from cut between S to A and S to B? We can take, no?
Sorry, what is your cut?
Cut between S to A and S to B.
Okay, so you are saying that take your T to be basically SCT, right? And basically S to be this, right? SCT. So
You mean,
see, so if you have to give me a cut, you have to give me two disjoint sets. So to give a cut, you have to give me two disjoint sets. So if you want to consider these two edges, so that means you are taking this as your cut, right? SCT in one set and BA in other, right? So let's see. So let's see if it is the case. So if we are looking at the capacity of this cut, so SB SA, right? CT. Okay, no. C. Yeah. This is also, so this is our new S. So what is the capacity of this cut? What is the capacity of this cut? So we
you
are,
have drawn this.
huh? Sorry. What are you saying?
So
Sorry. Yeah.
I can't see the cut of where you draw.
Okay. No, this is the cut. SCTBA. So basically, uh, okay. So this is the new cut. Purple SCT, and this is the one. So I am drawing the cut which is suggested by you only.
Ma'am, the one doubt, ma'am.
Yes, yes.
There is no direct edge between S and C and S and T. How we can take that in a same partition?
Sorry. Can you repeat your question? Yes. Yeah.
Ma'am, there is no edge between S and C and
Hmm.
S and T. S and T.
Hmm.
Then how can we take that SC and T in a same partition set?
So in we can take in it in same partition set, right? So it is not necessary. So as so so basically a cut is basically you are partitioning your two set of vertices into two sets.
Okay, ma'am.
There's no condition that, like, so if I'm taking SCT in one partition, there should be some edge within
No,
there.
I'm taking a cut where in first this partition only source vertex is there, and in S bar other four vertices are there.
Okay, you are taking that cut. Okay.
Yeah,
Okay, okay, we can take that one also. So you are basically saying, oh, this is also green and this is also green, right?
yeah.
So if we consider that cut, then also, yeah, it is a minimum cut. So sorry, then also, okay, if this is the cut, then what is the capacity of this cut? Capacity of this cut is 3.
Three only.
3. Yeah. So this cut is also fine.
Hmm.
Yeah. So see, minimum cut need not be unique. So this algorithm that I was telling you just give you one method to find a minimum cut. There can be different minimum cuts also. So in this example is basic. Your suggestion is basically showing that minimum cut need not be unique. Yeah. So okay, this was some different thing, but the aim of this example is to first, given any maximum flow, can you find a minimum cut? So is this clear to everyone? If you are given maximum flow, how to find the minimum cut, or are there any doubts?
And I was asking, if you get minimum cut initially, if you can find out minimum cut, then we can get maximum flow directly, no?
Yes, yes. I was mentioning. Yeah.
Sir.
So if you can find a
So,
minimum cut, you can find that directly.
so what is that method for finding minimum cut directly?
There is no method which works for all the like, I don't know of any method which works for all the example other than this. that we have mentioned. There might be, maybe I can check next time if there is any other efficient method. But right now I don't know.
Because what I'm asking,
Hmm.
if we get such a example in exam,
Hmm.
and if we are given four options,
Hmm.
then it will take time, no, to
Yes.
get the correct answer. We have to
Yes. But
find out all this. That's
yes,
why.
yes, yes. But if you'll get this in exam, if you'll get this in exam, they'll know that you'll use this method. So they would give you sufficient time to compute this. There will be sufficient time to come like.
Okay.
Okay, so is this okay?
And I want to
Okay.
ask one more question. If
Hmm.
only if only capacities are given
Hmm.
in a flow network,
Hmm.
and we have to and
Hmm.
flow is not given, only capacities are given.
Yes. Yeah.
Then can you assign the flow
Hmm.
by observing this conservation law and all these things, directions?
Yes, you can do that. Like if you can,
Then
yes, if you are, but make sure that you are choosing right flow. Like make sure that conservation law
uh,
is satisfied.
conservation law.
Yeah.
And then if I assign some numbers
Hmm.
following the conservation law,
Hmm.
and some other other fellow
Hmm.
follows some other flows,
Hmm. Hmm. Hmm.
assigning other flow,
Hmm. Hmm.
then maximum flow will be same for me and for other fellow.
Function might be different, but the value will be
Maximum
same. Value will be same.
value of
Maximum.
maximum flow will be
Yeah.
value of maximum flow will be same
Yes.
for both
Yeah.
of us.
Yes, both of us provided. Like, see, so you are just assigning a random flow. Then you have to check. Then if you're assigning a random flow, then you have to then you have to draw that residual flow diagram. And if there are no
Uh,
augmenting paths, then you can claim that this is the maximum flow.
okay, but the
So
answer will be same
yeah,
uh, for me and others.
yeah. The value of flow will be same.
Value of flow will be same. Okay.
The function might be different.
Okay.
Yeah, so but that, like, see, either you can do that, but if there are a lot of vertices, then maybe finding a function might be difficult. So you can use that algorithm. You first consider the flow with the trivial flow, that you assign zero flow to each of the edge. Then you look for an augmenting path, and like even if you are not by observation, if you are not able to find some flow which is satisfying those two rules, you can start with initial flow 0 and then apply that algorithm to get the maximum flow. Is that fine?
Yeah.
Okay, so now if we know what is minimum cut maximum flow, let's do some questions quickly. Okay, so this is this. Okay, so so if everyone understood what is the how to construct residual flow, we can skip this question and we can directly go to the capacity. Can I skip the construction of residual flow, or should I do it?
You can skip.
You can skip, ma'am. No need.
Is everyone okay with me skipping it? Because we have construct, like we have done one example where we did construct. So okay, okay, maybe like I'll skip for now, and if we have in the time in the end, then I'll come back in. So this was so you can see that first question is to find the residual flow. So first question is to find the residual flow for this network, and it I have constructed this, so it will come out to be this. So it will come out to be this. So like let me so see, SA had flow and value and capacity value which were same. So there was only a backward edge, and we have done this for all the edges. Now once we have constructed a residual flow, the next part is to find the capacity of this following path. So what is this path? Se ef se ef fi
F I
ij.
I J
Okay, sorry, this was an error. Ij,
J G
Jg, and ct sorry, Jg, Gc,
G
and
C C T.
ct. So in this example you can see, there are both forward and backward edges. So augmenting path need not have, like, so that previous question, that if augmenting path should have all the forward edges or the backward edges. So this is an example of an augmenting path which is consisting of all both type of edges. So now this is the augmenting path. So what is the capacity for this augmenting path?
1.
One number.
Yes, what is, because we are taking minimum over 8, 5, 2, 3, 1, 1 and 2. So
Two.
capacity of this path is coming out to be 1. Okay. So one, we have done this. Now, okay. So is this, I think this is clear. Okay. So now next part is, so we have this flow diagram, and we also have the same augmenting path with capacity 1, which we have find out in the previous question. SEF IJ JG GC and CT. So now we have an augmenting path with path capacity 1. So how do we construct the new flow? So what will be our new flow?
You have to add 1 in the edges.
Do we add 1 in all the edges?
Not all edges. On the
The edges in the augmenting
augmenting path.
path.
Edges in the augmenting path plus the edges in the forward direction. So see, now, so first edge is SE. This is an edge in forward direction. This is an edge in forward direction. So now, hence we'll add 1 to this edge. So first flow value was 3. So now this flow value will become 4. So f prime of SE is 4. What will be now the next edge in the path is EF. It is also in the forward direction. Therefore,
11, 15.
this is also in
11,
the,
15.
yes. So 10 plus 1, 11. So this is 11, 15. Now the next edge is in the next edge. See, next edge is in the reverse direction. So now we won't add 1, but we will subtract 1, because it is in the opposite direction. So now FIF will become 2
1.
minus 1, 1. So see, that's why we have to keep track whether the edge is in forward direction or in the backward direction. So this will be 1. We cannot, so this we cannot add, and you can see we cannot add 1 to this edge also, because it has already, the capacity is 2, and capacity is 2. It cannot have flow value which is bigger than 2. So now the next edge is IJ, which is in the same direction. So we'll add,
7, 9.
it is 7. Next edge is, now the next edge is again in the reverse direction. So what will be the new flow?
0.
Yes, 0,
0,
5.
5.
So this is 0, 5. And next is, it is in the same direction. So this will be
1,
1.
1, 1.
1. And now this is also in the same direction. So it will be 11.
11.
So now this is important. So is it clear to everybody? So when we are given an augmenting path, so we are pushing the path capacity, but we add path capacity if it is a edge with the forward direction. But if it is an edge with backward direction, then we subtract the path
Okay.
capacity. So is everybody uh, okay with this question number 5?
Yes.
Okay. Okay, if everyone's fine, then let's move to next question. So now we have to find the maximum flow in the previous problem. So first I have recalled what were the state, what are the state. So this was our initial flow that we were given. Now from this initial flow we are trying to find the maximum flow when we are given some initial flow. So this was some initial flow. So what is the algorithm? Given an initial flow, construct a construct a residual flow diagram. After constructing residual flow diagram, next step was to find the augmenting path. Augmenting path was this SEFI, this one that we were talking about. After finding the augmenting path, we push the path capacity, and we push the after pushing path capacity, this was the new flow. So we see that these values were getting changed. The path, these were the new values which are changed. And so initial flow, what was the value of initial flow? We computed this initial flow was
23.
823, right?
Yeah. Now it becomes 24.
Now it becomes 24
24.
because 8 plus 4, 12, 8, 20 plus 4. And also you can see when we are constructing new flow, it the flow value increases by path capacity always. So path capacity was 1, so 23 plus 1 is 24. Now after this was the new flow. Now once this was the new flow, the next step is to again draw the residual flow diagram. So we can use the previous residual flow diagram to construct the new residual flow diagram. We have to just make changes to the edges appearing on, we have to make changes just to the green edges. So you can use the previous flow diagram and make the required changes in the new edges of the augmenting path to get a new residual flow diagram. And now in this residual flow diagram, can you find an augmenting path? Now in this new residual flow diagram, this F prime, is there an augmenting path in this new diagram?
No, ma'am, there is no
No,
augmenting.
there is
Yes,
no augmenting path.
because if we are trying to find an augmenting path, we'll start from SE, then we go to EF. But after EF, we have nowhere to go. So there is no augmenting path. And if there is no augmenting path, what does our algorithm say?
Stop.
Stop. So therefore, this is the maximum flow. Okay. Now, so does everyone agree that maximum flow is 24?
Yes.
Yes, ma'am.
Okay, good.
Yes, ma'am.
Okay. Now once we have found the maximum flow, now we do the okay. Sorry, there was. So now once we have found the maximum flow, next question is to find the minimum cut. So given a maximum flow, this was the maximum flow and this was the residual flow diagram. So what was the algorithm to find the minimum cut using the residual flow diagram?
10, 7, 7. Occurred between B to C, F to G, and I to J.
Okay. So basically, the S will have all those vertices where so we'll write down all those vertices which have a path from S to that vertex. So do we have a path from S to A? Is there a path in residual flow diagram from S to A? Can you find a path in residual flow diagram from S to A?
No.
No, ma'am.
Is there this is it this is a path, right? SEEA. There is a path SEEA. So it is not necessary that path should have all the forward edges or all the backward edges. So since we have a path from S to A will be there. So is there a path from S to E? Is there a path from S to E?
Yes.
Yes, the
Yes.
edge SE itself. So this will also be here. Is there a path from S to H?
Yes. S
What?
to E, E to H.
Yes, very good. S to E and E to H. So this is also there. Is there a path from S to I? So we have a path from
Yes.
S to H.
Yes, ma'am.
So
Yes.
that S to H and H to I. So we have a path from S to H, then we go to I. So there's also a path from S to I. So this is also in S. Now, now do we, okay, so now do we have a path from S to F? So we have a path from S to E, and there's a edge going from E to F. Therefore, we also have a path from S to F. So F also will be there. And what about B? Do we have a path from S to B?
No, ma'am.
No.
No S to P.
No path from S to B. So this will go into S complement. So what about G? Do we have a path from S to G?
Oh, no. No.
No. So this is also in S bar. What about S to J? What about S to J? Do we have a path from S to
We
J?
have path, ma'am.
Yes, ma'am.
Yes,
Yeah.
ma'am.
What?
Which path? So we have a path from S to I, then we go from I to J. I to
I
J.
to J.
Okay. And what about rest of the vertices? Do we have a path from S to C?
No, ma'am.
No, ma'am. No.
Okay. And we know we don't have a path from S to T because this had no augmenting path. Oh sorry, these are red. S C. So our claim is that this is the minimum cut. So we have found the, so we can see that also this will come out to be minimum cut. How can we check, how should we check that if it is a minimum cut or not? We find the capacity, and if it is a minimum cut it should come out to be the flow value, which is equal to 24. So is the, so this is our cut, so this is our cut. So what is the capacity of this cut?
24.
24. We are
24.
taking this edges AB, this, this. So it is coming out to be 24. So we see that this is indeed a minimum cut. Okay. So this was the last
We
quick.
can take
Yes.
we can take cut straight way, a cut a straight line between vertex B and C, F and G, and I and J.
Uh, what cut you're saying? Yeah.
A cut line between vertex B and C, F and G, and I and J.
Yes. Okay. This one. This one.
Yeah,
Yes. If we
it
take,
is 10 plus 7, it is for 24. No,
okay, 7 plus 7, 24. But there's also a 10 now.
no, it 10 plus 7 plus 7. No,
Okay, sorry. Okay, 7 plus 7, 4. Huh. This is a, okay. Yeah, this is also a, okay, wait, let me think. Yeah, these are the only edges, right? Yeah. So this cut is also valid. Yeah. So you see, minimum cut is not unique. That is true. That minimum cut is neither the maximum, only the flow value of minimum cut and value of maximum flow is unique. Neither the flow function is unique, neither the minimum cut is unique. So yeah, this is also a minimum cut. So see, by observation you are getting that this is a minimum cut. But like if you are by so this so if so but the question was to find the minimum cut appearing from that flow diagram, so we did this procedure. But if you have to find just any minimum cut, then this will work. This so this is fine. Are there any questions in this? Are there any questions here?
Ma'am, in that to find the minimum cut, you have taken that vertices which are linked to S as a one partition, and the other vertices as another partition.
Yes.
Uh, so that will give the minimum cut, right? Which
Yes.
is equal to that maximum flow.
Yes. Yeah.
But if we avoid any one such vertex which is linked to S, we don't get that value equal to that maximum flow.
No, it need not be that. Like that that is not necessary. This is just one method. So see, he's like he suggested this. He suggested you take your S to be all these vertices. If we take S to be all these vertices and S bar to be these vertices, then also this is the minimum cut, because you see the edges in this cut is BC, FG. Okay, this is not a minimum cut. See, oh, because we have to add out the capacity, not the flow value. So in your question, this was not the minimum cut.
Huh?
Your sorry. So you were this is not the minimum cut. The cut that you have suggested. You are suggesting this cut, right?
Huh. You have
But
to add capacity or you have to add flow?
we have to add the capacity.
Capacity.
Yeah. So this is not the
Okay.
minimum cut.
Okay.
The one you have suggested.
Mm-hmm.
Also, okay. So maybe we did this error previously also. Let me check. So in this also, we said that this is the minimum cut where S. So no, so so previously also we were sorry, we did this mistake. When we are computing the cut value, we have to add the what did I? We have to add the capacity. So there was a suggestion that we can take our cut to be S and all the other vertices. But if we look at this, the capacity of this cut is coming out to be 5. But the flow value is 3. So this is not a minimum cut. We have to add the capacity, not the flow.
Okay.
Sorry, there was an error. Please. So
That means minimum cut is unique or
no, but
what
then
is it?
also minimum cut is not unique. Okay, we'll have to look for examples, but minimum cut need not be many. So coming back to Retrieval's question, so what was your question? Can yeah.
Ma'am, I
Yeah.
have one question.
Yes.
You have taken that vertices which are connected to S as one set and the another
Uh,
set which is disconnected from S.
yes. I took that. Yeah.
Okay, ma'am. So what is my question means whether this only minimum cut will be equal to that maximum flow.
No. So see, I right now I'm not like wait. The cut need not be unique. Cut
Okay,
need
ma'am.
not be unique. So this is just one way to find a minimum cut, but there can be other minimum cuts.
Okay, ma'am. But
Yeah.
that B we can whether we can take that B as also in that first set
Okay. Let's see that if we can do
because
that.
it's not connected to S, right?
Yeah. So it is not connected to S. You are right, but you are saying like we consider this cut. Okay. Let's see if you we can see that. Okay. Uh, so the other suggestion is that we take our S to be S A E H I F and B also, right? So if
Yes,
we
ma'am.
take,
Yes.
so if we make this also as green, so basically now our cut is this. So let's see. So if we have to say that this is a minimum cut, if the capacity of this cut is coming out to be 24, then we can say that this is a minimum cut. So is the capacity of this cut coming out to be 24? So what all edges we have to consider? We have to consider basically BC, FG, GJ and JT, right?
Yes, ma'am. Yes.
BC. Wait, not GJ. Not GJ because this is a uh, not GJ because it is in the other direction. GJ is in this direction. So we are not considering. So we can only take BC, FG and JT. So is there any other edge? Am I missing something? Oh, okay. Yeah, so these are the only three edges. See? So but then the capacity is coming 7, the capacity is coming 7, 14 plus 11, right?
Mm.
So this is capacity
Yes.
of this cut is coming out to be 25. So
25.
so
Yes.
this is not a minimum cut.
Yes, ma'am. That's my doubt, ma'am.
Yeah.
Because you have partitioned the set as a first set has a link with the source. The vertices which are linked to the source has been taken as a one set,
Yes, yes.
and the other set is a partition which is not connected to the source set.
Yes.
So we are getting the minimum cut, which is equal to the maximum flow in this.
In this diagram. Yeah. In this
Yes,
diagram.
ma'am.
Yeah.
My question is what means whether the no other cut than this will be equal to the maximum flow. Is that right, ma'am?
No. So I'm
No
saying that
other minimum cut.
no, I'm
Is there
saying
any?
no, it is not necessary that. So maybe in this example we are not able to find some other cut whose value is not 25. Since minimum cut is not unique, there can be some other cut which has
Okay.
capacity 24.
Okay, ma'am. Okay, ma'am. Okay.
This is just one method to find a minimum cut.
Okay, ma'am. Ma'am, one more doubt, ma'am.
Yes, yes, yeah.
In the assignment 7, the fifth problem, ma'am.
Fifth problem, yes. Uh, Assignment 7.
Yes, ma'am.
So, okay, wait, let me share my screen. So fifth one is this, right? Resulting flow.
Resulting flow value. Yes, ma'am. Yes, ma'am.
So we did this question, right? We were getting 24.
Yes, ma'am. That's my doubt.
Yeah.
In that question, you have said that we have to consider the path in problem number 4.
Hmm. Yes.
Whether we have to find the resulting flow value in that residual network or the
No. So basically, so this question is basically saying your fifth question. So if I like for, so fifth question is that consider the path P in problem 4. Push del G units of flow along this path and the resulting, you have to find the resulting flow value, right?
yes, ma'am. Yes.
So basically, so pushing del G units means that what I was doing previously. So this was this. So in the fourth question, we've got this following path, and the capacity of this path was coming out to be 1. So the fifth question is saying push this del p units along this path. So pushing this del p units along this path means that basically you have to consider all the edges which are appearing in this augmenting path, and you have to consider all these edges which are appearing in the augmenting path. Wait.
Okay, ma'am.
And then if that edge is in forward direction, If that edge is in forward direction, you add del p units, and if that edge is in the backward direction, you subtract del p units, and all other edges which are not in the path have the same flow value. So now after applying that thing, you'll have a new function f. You will have this new function f prime. So we did this, right? Now you have to find the flow for this function, and flow for this
Okay,
function
ma'am.
was coming out to be 7 plus 6 13 plus 11 24. Okay, is was this your question?
Yes, ma'am.
Okay.
What edges you have taken, ma'am?
Yes, okay. So I'll repeat this question. So this was our augmenting path, right? S E E F F I I J J J
IG.
G G C and C T. So now see,
Yes.
this S E edge, this S E edge is in the forward direction. So the earlier flow value was 3, and this is a edge in forward direction, so we add the path capacity. So the new path capacity is 4, which is 3 plus 1. Now the next edge is ef. Ef has flow value 10, and it is the edge in forward direction, so you add 1 and you make it 11. Now but next edge is fi. This edge is in the opposite direction, so it has
Okay,
flow
ma'am.
value 2, so you subtract the path capacity, and you do this for all the edges in appearing in the path, and the edges which are not appearing in path remain, their flow value remain the same. So,
Okay, ma'am. Okay, ma'am.
and
Now I
once,
understand, ma'am.
once you do this, you get this new flow. So this is the algorithm only. So you start, so given any network, you assign zero flow to each, or any, you start with any flow, then you construct the residual flow diagram. From the residual flow diagram, construct an augmenting path, and from that augmenting path, construct a new flow, and you keep on constructing this new flow until you get a flow which has no augmenting path.
Okay, ma'am. So if we get any question like this, delta push delta G
Huh, yeah,
units of flow, we
yeah,
have to
yeah.
add that one to all augmenting path values.
So you have to add the path capacity to all the forward edges in the path, and
Okay, ma'am. And subtract from
subtract path
backward edges.
backward
Okay.
edges in the path, only in the path, and all the rest of the edges which are not appearing in path have the same value.
Okay, ma'am. Okay. Thank you.
Yeah.
Thank you.
Yes. Any other questions?
Ma'am,
Yes. Yeah.
the adding and subtracting forward backward means you can see that first diagram, that is the first network diagram, right? Not
Yes.
a rest network
Yes.
diagram.
Yes. Yes. Yeah.
Okay. Okay,
Yeah,
thank you.
yeah, direction, like, see, so adding and subtracting, so we look at the, so we have construct, when we are constructing residual flow diagram, when you're
Okay.
constructing this residual flow diagram, there are two type of edges: forward edges, uh,
Yeah, backward edges.
and
Right.
backward edges. So if
Mm.
so so when we are pushing del p units, so basically we are adding to the forward edges path capacity, and subtracting path capacity from backward edges only in the edges which are in the augmenting path.
Okay.
The
Okay.
rest of the edges are not changed.
Okay, fine.
Yeah.
Thank you.
Yes. Any other question?
Ma'am, the
Yeah.
doubt she has asked, I have the same doubt, ma'am.
What?
We have to add and subtract the values from that first diagram, not in that residual flow diagram, right?
Yes, 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 from the first diagram, because this is your original flow. Yeah.
Okay, ma'am. Okay.
So yeah, okay. Now I got it. So her question was that if we do that, we don't look at the residual flow diagram. We are adding and subtracting has to go from the original diagram. Yeah, yeah.
Okay, ma'am.
So
Thank you.
see, this 3 becomes 4, this 10 becomes 11, and this 2 becomes 1. So yeah,
Yes, ma'am. Yes.
okay. Any other question? Okay, so if there are no questions, then we'll meet next time. Okay.
Ma'am,
Yeah. Yeah.
next Sunday we will have exam, no, ma'am.
Oh,
So when
oh,
will be the class
okay. Yes,
before
yes,
that?
yes, yes. I note. So I noticed that. So I'll ask the NPTL people to either conduct the class on Friday or Saturday. Is that fine?
Okay, ma'am. Okay.
So the
Okay.
next class will be either on Friday or Saturday. Yeah.
Oh, thank you, ma'am.
Okay.
Thank you, ma'am.
Yes.
Thank you, ma'am.
Yes. Yes. Yes.